This meeting is being recorded.
In this video from chapter 17 on additional aspects of aqueous equilibria, we're going to take a look at how we can use the Henderson-Hasselbalch equation to find pH of a buffer system. So that's what we're going to look for. And we can also use that same equation to solve for other things, but specifically pH for this first equation. So if you watched the previous video, you saw the derivation of this equation, but I'm going to write the final form here. So we have pH equals pKa. We're going to have plus the log of our base over acid. All right, so this is again the best form to utilize this equation. So when we're solving for pH, the hardest part of this is figuring out which is the acid and which is the base. So in this case here, we're told that we have lactic acid. So this one's pretty obvious. This is the structure here, in case we wanted to know that. But we don't actually need that for our calculation, so that's just additional information. But we will need to know our anion here, right? Our sodium lactate is our conjugate base. So, and we're also given Ka as well for lactic acid. So with all this information, we can use this equation here by solving for pH by plugging in the negative log gives me pKa from Ka, so I'm going to use that value for Ka, 1.4 to the negative 4. So now I have pKa where I need it, and then we're going to have, we have to identify, right, this is my acid concentration, and then this is going to be my base concentration, so we're going to add to that the log of my base, so 0.10 over 0.12 for my acid. And what happens here is, since the acid is the higher number, we're going to add the log of a value that gives us, rather, this negative value here. Oh, lost control, apologize there, of my stylus. So we get this value here, this negative 0.8, when we plug in this to the log equation. So we're going to get our rearranged or our rewritten equation here. Negative log of this value gives me about 3.85. And then I'm going to add to that this negative value. So I'm going to subtract 0.08. So my pH of this buffer system with these specific concentrations of my weak acid and weak base will give me 3.77. All right, let's take a look now at this second sample exercise here for a buffer system. And now we're asked to calculate the concentration of sodium benzoate that must be present in a 0.2 molar solution of benzoic acid. So this is my acid. This must be my base. Here's the formula of the acid. To create a pH, so we're given pH of 4.0. So this is our pH value here. And we're also given Ka. So we can rewrite the Henderson-Hasselbalch equation down here, just in case, right? Just so we can keep track of what we're doing. So plus our log of our base over acid. All right, so now I know pH is 4.00. I know pKa, I can get that from the negative log of 6.3 to the negative 5. And then we're going to add to that the log of our concentrations, the ratio here of base to acid. So sodium benzoate is my unknown, so I'm just going to plug it in B. My benzoic acid is 0.20 molar. So we're going to end up rearranging this equation a little. So let's see, we have 4.2, oh, sorry, we're reading the wrong side. So 4.00 is going to equal, when we take the negative log of this, we get 4.20. And then we still have this portion's unknown, b over 0.2. So we can separate this portion of our equation here. So we can have, we subtract 4.2 first from both sides to get, we can combine like terms here, so we get negative 0.20 is going to equal the positive log of our base concentration, and then this is in the denominator, this 0.20, so this will be minus the log of 0.20. This is a a logarithmic expansion, so when we have something on top of something, when we write it down here, it's no longer division, but it would be subtracting one log from the other. So this is our rearranged form, so I'm going to try to squeeze this in up here. So now if I take the log of that 0.20 value, I'm going to get this here, so negative 0.20 on one side, log of b, and then this gives me minus, this value is also negative, so make sure to keep track of your negatives, 0.699, and then so this is really like positive 0.699. So to combine my like terms, I'm going to have to actually subtract 0.699 from both sides. So finally, I get negative 0.899 is equal to my log of my base. And then to take the antilog or reverse the log, we can raise both sides 10 to the log of b. So this reduces to just concentration of base. And then we do 10 to the raised to the negative 0.899. And that will give me a concentration of roughly 0.13 molar.